Hi Spring fans! In this installment we're going to talk about GraalVM and Spring Native, but first let me tell you a story. I was walking through a forest and I found some mushrooms that I consumed, and then I grew very, very small. Oh wait a minute, no, that might have just been a weird dream I had. Or was that the beginning to Alice in Wonderland? It doesn't matter, I still feel like the story is pretty appropriate because GraalVM makes me sometimes feel like Alice in Wonderland. What's GraalVM? Well, GraalVM is a open JDK distribution with some promising extras. GraalVM comes from Oracle Labs, a part of Oracle, who are coincidentally the same folks that drive a lot of the work being done on Java and OpenJDK itself. Java is awesome and GraalVM is awesome, but they are not the same thing. Or at least, they're not the same thing for the moment. Hopefully, Project Layden, which strives to bring AOT support to the OpenJDK platform, will see a convergence of functionality. But for now, since we can't really speculate on that in middle of 2021, let's just talk about GraalVM. It's the tool to know anyway. GraalVM started off as a faster just-in-time implementation, so a just-in-time compiler that was implemented in nice, clean, refactorable Java code that had hoped to replace the creakingly old spaghetti C++ code in Hotspot. The just-in-time compiler analyzes code at runtime and turns frequently accessed code into native architecture-specific binaries. So while your application may start as purely interpreted Java bytecode, it might end up as a mix of architecture and operating-specific native code and interpreted bytecode. The process is usually transparent to the developer. It's just one of the freebies that Java developers enjoy for using the JVM. The result can be applications that, for certain hot path scenarios, may run many times faster than the equivalent interpreted bytecode. Large organizations know about this dynamic and sometimes try to leverage it. Some, like Google and Alibaba, won't even put services into production until they've been warmed up. The resulting application goes through a lot of different runs to exercise certain code paths to trigger the just-in-time compilation. These applications run very quickly and can even in some cases outperform equivalent C or C++ code because the just-in-time compiler can do whole code-based optimizations that we may not be able to take advantage of when we write our native C and C++ code. You can use GraalVM as a better just-in-time compiler if you like, but GraalVM has a few other party tricks. One GraalVM feature that's super interesting is a Polyglot Runtime that lets you run artifacts from different languages like JavaScript, Java, Ruby, R, etc. in the same runtime. So imagine defining R functions, then injecting a reference to that function in your Spring Boot application. Yes, that's a thing I can say and do, that's not crazy, in 2021. Neat. GraalVM has this nifty new feature called the Native Image Builder. The Native Image Builder is an ahead-of-time compiler as opposed to a just-in-time compiler. If having your code retroactively turned into native code at runtime is cool, then surely having all of your code proactively turned into native code is even cooler? So let's review some vocabulary. When we talk about compilation in the Java platform, we're typically talking about taking our Java source code files and turning that into bytecode, .class files. Just-in-time compilation refers to turning your runtime code as the program is running and finding the frequently accessed code paths and then turning those particular segments of code into native code. And then ahead-of-time compilation turns all the code at compile time, including all the bytecode in the class path, into native code proactively. The Native Image Builder is an ahead-of-time compiler. It chucks out everything that it has determined isn't being used at runtime. I repeat, this is important. It throws out everything that it determines during static analysis at compile time that it thinks is not being used at runtime. This process takes a long time because it's not just compiling our Java source code files, but also compiling all the .class files into native code and analyzing which code is used and when. The resulting architecture-specific binary is small, very small, like Alice in Wonderland small. It includes only the minimum JRE and the minimum types from all the libraries on the class path that are required to support the application. The resulting applications tend to start in milliseconds and take tens of megabytes of RAM, not hundreds, or, worse. It's possible to get a Spring Boot application with data access and a web server and a Java runtime, not exactly a JRE, but you know, something like that, that's less than 20 megs of space on disk. This is phenomenal. GraalVM really is a wonderland. But just as they did for our protagonist Alice, things get, well, you know, weird when our applications get that small. Java's a funny old thing. It feels like a more stodgy systems programming language when compared to languages like Ruby, Python, JavaScript, etc. But it feels very dynamic compared to something like C or C++ or Go. It has a runtime, and it has the ability to answer questions about its own state. You can dynamically generate new classes or interfaces at runtime and load them into the class loader, then use reflection to, with just the string name of that generated class, dynamically instantiate an instance of that class. And then if you generated an interface, you can also generate a Jdk invocation handler based proxy that gives you an object that implements the interface. And then you can invoke that code using nothing but strings if you want. And then, if you wanted to, you could also then take that object and serialize its bytes to disk or to database, or load it into another JVM over the network. The possibilities are endless. All those things may be done after the application has been compiled, started, and is running. And so perhaps you're beginning to see the problem. There's no guarantee that GraalVM will see or understand all this dynamic behavior. Especially at compile time, when it does its static analysis. It might throw away all the code that would later on be used by these dynamic behaviors and that are required to support those things at runtime. GraalVM is what we in the highfalutin framework business call a party pooper. So GraalVM supports configuration through a Java API, through JSON files, and through command line switches that clue GraalVM to the particular behavior desired at runtime. If you want to create a Jdk proxy, you can put an entry in the appropriate JSON configuration file, and GraalVM will pre-compute a type that implements all the interfaces that you specify, and then bake that into the memory of the native image heap. Then, at runtime, when your code tries to build a proxy using those types, those interfaces, GraalVM will hand you the pre-computed type. The possibilities are there, certainly, but as you can imagine, this can quickly get tedious or exhausting if you're building on top of more dynamic abstractions like Spring. So, what we want is some way to automate all of that. And this is where Spring Native comes in. Spring Native knows about the scenarios in which your applications and which typical Spring Boot applications might need configuration, and it provides that configuration for you so that we don't have to do that ourselves. It's awesome. The goal with Spring Native is that you can bring your application unchanged and get a GraalVM native image. In this video, we're going to look at GraalVM and Spring Native, and we're going to see how they can help us deliver our tiny applications for big systems to production. And sure, things are going to look a little different, but at the end of the day, it's still Spring. Alice said it best. I knew who I was when I got up this morning, but I think I must have been changed several times since then. This rabbit hole is deep and very interesting, so let's get started. Let's talk about how to install GraalVM on your local machine. One thing you can do is to go to graalvm.org and then download either the GraalVM Community or the GraalVM Enterprise edition of the software. I chose the Community version. Choose Download from GitHub. It'll take you to a page where you can find different variants for your operating system and the version of Java that you'd like to use. I am on Mac OS and I'm using Java 11, so I chose that one. Once you've downloaded it, you're going to want to make sure you install it like you would any other open JDK distribution. Set up a directory, add that directory to an environment variable, or reference that directory in an environment variable called Java_home, capital letters, and then make sure that Java home/bin is in the path for your operating system. Another option, if you have a package manager on your operating system, is to use that to install this OpenJDK distribution. One very popular option in the JVM is SDKman. SDKman is a JVM specific ecosystem tool. Just say SDK list Java. It'll show you all the different virtual machines that you have. I have got the GraalVM 21.1.0 R11 version of GraalVM installed. So you can see it's already installed. You just say SDK install Java and then the particular version. You can go a step further and make it the default version of Java by saying SDK default Java and then referencing the particular version. And with that, we've got GraalVM installed. Let's take a look at the basics. We're going to start with the absolute default bare minimum configuration that you get if you were to go to start.spring.io today. We're just going to build a traditional application, an imperative traditional kind of application. Maybe imperative is the right way to think about it. We're going to use JPA, we'll use H2, we'll use Lombok, we're going to use the web support, etc. And then finally, most importantly, we're going to bring in Spring Native, the experimental Spring Native. Okay. Hit generate. Let's open this in the IDE. And this is just a traditional imperative non-reactive application. I'll do a reactive example in just a second here, but what you need to understand is that this just works, right? So private integer ID, private string name. This is going to be using JPA because I make terrible life choices. So here we go. And we're going to create a repository to manage that data. Customer integer. Alrighty. Let's write some data to the database. As usual, we'll create a little schema and some data. Okay, so there's some people that I'm going to write to the database. So now, if we build a little REST endpoint, okay, I just want to inject that into a constructor that I'll synthesize here using Lombok, which is a compile time annotation processor. All right, so there's our basic REST API. Let's just run it locally to make sure that that works as we expect. Oh. We need to put the @entity annotation and restart. Oh, and the other thing I want to do is I want to disable Hibernate's DDL, right? So false, auto. Okay. Just in case. Let's try this out now. So localhost customers, and voila, there's our data. It's worked just fine. The application starts in 1.7 seconds. Keep in mind I'm screencasting. Now I want to build this into a GraalVM native image. Well, that was an adventure, but it's built. Let's check it out and see what happens. We've got a Docker image here, right? This Docker image was built through something called a build pack. So when we generate a brand new project on the Spring Initializer, it gives us a configuration that sets up the Spring Boot Maven plugin, which in turn sets up the native image build pack builder. The core conceit of build packs is to containerize your applications. No, I didn't say we have to use YAML or Docker files. Don't freak out. That's not what I'm all about. I don't like those things. They waste time, they're bureaucratic, and they're needless. The whole idea is that there are only so many different ways that we have to containerize a given application. So why reinvent that? That's what build packs help you do. It's a cloud-native computing foundation project. It's a technology that you can use if you want to go to buildpacks.io to find the specification. And there's an implementation called Paketo. Now, Paketo is part of the Cloud Foundry Foundation, and it has builders for different languages. So given an artifact, it'll turn into a container. Build packs are originally the work of Heroku, the pivotal Cloud Foundry team, and working with Heroku eventually embraced that work and eventually worked together. They collaborated on something that would become cloud-native build packs, right? The thing that we see today. So the earlier versions are similar, but not exactly the same. It's now a cloud-native computing foundation project that you can use. You can use to easily turn your application from something trivial into something that's ready for production. All right, so we've got that image. Let's run it. I want to run it on port 8080. So the application's spun up. It's available. It's started up in 163 milliseconds. Oops, actually, just refresh this page. There you are. All right, we looked at traditional imperative I/O. Let's look at a simple reactive application. We're going to bring in Spring Native. We're going to bring in H2. We'll bring in the reactive web support. We'll bring in R2DBC. We're going to use Kotlin, and we'll hit generate. We can use Kotlin because why not? Alrighty, we've got a basic class, public static void main. Let's build a entity using a data class. This is kind of like a Java record, except it's, from a decade ago. We'll have a annotation to mark it as a primary key. We'll create a repository to handle the tedious, soul annihilatingly boring read, write, update, and delete data management lifecycle. And then finally, we're going to create a REST controller. And here, rather than doing that the old-fashioned way with a REST controller, I'm just going to create a functional reactive endpoint here, except I'm actually not going to use even the functional reactive stuff. I'm going to use the functional reactive stuff within Kotlin's coroutine library. So I'll say co-router. Create an endpoint here. Server response dot OK dot body value and weight. Body and weight. And we'll say ref customer repository dot find all dot to or as flow rather. Alrighty. So there's our coroutine router. Let's run this. We need some data before we can do that though. So we'll say data.sql insert into customer name values Josh, Andy, Sebastian, Olga, Violetta, Yushin, Madura, Dr. Sire, Spencer. Okay, so there's some names. Now I need to create the table schema. Now we'll start the application. Okay, it's up and running, 1.3 seconds, already markedly faster than traditional imperative I/O, even on just the JVM. Now we're going to turn it into a native image with GraalVM. So let's use the build pack base build again. We'll say maven clean package spring boot build image. All right, our application is built. It's ready to use. Let's run it as before. So we'll say docker run. All right, and the application starts up fairly quickly in 83 milliseconds, so less than half, or roughly half of what the previous application started up with the same functionality. Let's take a look at what's happening when we compile our applications using Spring Native. So let's start again at the Spring Initializer. We'll create a new application here, and we're just going to call this the AOT project. We're going to download that and then open it up in our IDE. All right, so as before, we'll add a simple runner. And we're going to compile it. As we reviewed, GraalVM has two different types of compilation. It's going to take our Java source code and turn it into bytecode. Then it's going to turn that bytecode into native images. And we talked about how when we pass everything into that AOT compiler, the native image compiler, we can provide configuration. Well, we can actually preview that configuration without actually running the compilation. And the reason is because with Spring Native, we have a new plugin called the Spring AOT plugin that gets configured automatically for you in addition to the build pack support. That Spring AOT plugin is the thing that actually generates the sort of configuration that'll be passed to the Packetto build pack for the compilation. So we can actually preview that without actually doing the work. So let's recompile this. We can kind of do a dry run of the compilation without actually waiting for the full native image compilation process to finish. That way we can see what configuration was generated for us and what's being fed into the GraalVM native image compilation process. Okay, the process is completed and drastically quicker than it would have if we had to wait for the full process. So if we go to the target directory now, we can see that we've got in the classes directory a meta-inf folder wherein we find another folder called native image. There you'll find hints files and properties that we expect to be passed to the command line. We also find that there have been some generated sources that have been created for us. And I think this is one of the most interesting parts of the AOT framework that we've set up here. Spring Native does transpilation for certain things. So you may know, if you've ever looked into the internals of Spring Boot, that there's a text file called spring.factories. And spring.factories is a service loader. Basically, it's a list of things that Spring will start up when the application starts up. And you can see that lots of different jars have them. The most prominent of them, I think, is probably the one inside of Spring Boot Auto Configure. And there you can see it says org Spring Framework Boot Auto Configure, Enable Auto Configuration. And there you've got all these different Java configuration classes. Well, these Java configuration classes themselves depend on other things being present on the class path. So while you may not be able to see it here, I've got red ink on my screen. I've got red type on my screen suggesting that these types are not in the class path. That means that this will fail, and so there's no point in trying to run this at runtime. And so GraalVM, the Spring Native compilation through GraalVM, actually prunes this stuff from the class path before it ever gets to the point where it's going to be evaluated at runtime. That makes for an extra boost in performance. Another thing that we can do is we can evaluate these conditions, and we say, okay, if this type rabbit-template.class is on the class path, then load this configuration. So rabbit auto configuration is one of many different examples of an auto configuration class. These are regular Java configuration classes that get loaded when the application starts up. there are conditions that guard against their activation unless certain types are on the class path. So for example, RabbitTemplate.class and Channel.class need to be on the class path before Spring Boot will try and run these. Well, of course, in a native image, there's no such thing as a runtime class path versus a compile time class path. That is to say, once you've compiled it, there's no changing the class path. It's just, it is what it is. There's no DLLs, so to speak. There's no jars as libraries that you can swap out externally. So, when you run this code will be evaluated at runtime, but what's the point? We already know at compile time whether this type is going to be there. And so Spring Native proactively prunes this from the call graph, from the object graph, before the application is even compiled. We do that by evaluating all these auto configuration classes and all these conditional on class annotations. The other thing that's kind of interesting is that there's a text file, this spring.factories that I just showed you, that gets evaluated at startup time. But of course, this doesn't represent the final state of the service loader as GraalVM will see it, because we, as we just talked about, we remove certain things. So Spring AOT will automatically create a set of Java classes that do basically the same thing. Right? You can see that here. And this is a Java version of the same thing. So there's no strings, there's no resource loading, there's no reflection, nothing like that. Everything in this class, by virtue of the fact that it's a Java class, it's Java code, gets compiled, much easier for the GraalVM compiler to process. We can take advantage of this mechanism. Let's go back to our application here, and we're going to create a configuration class. And we'll have an application runner in here. Conditional runner, and we're just going to print out hello conditionally. Okay, and so this is going to be a Java config that we're going to put in a separate package. I'm going to load via the service loader mechanism as sort of auto configuration, and we'll take this and put it there. And we'll go here and we'll create a meta-inf directory. Create a new file called spring.factories. Enable auto configuration equals auto configuration com.example auto configuration dot demo configuration. Okay, so now if we run this process again, you can see hello AT and hello conditionally. Okay, so now let's go to the generated configuration there, and we can see that our Spring Factories has our custom auto config demo configuration. Okay, so it's registered there. Now let's add a conditional that could not possibly evaluate to true. So for example, conditional on class, and I think we can use, let's see, what class do we know for sure isn't here? JDBC. So that type doesn't exist on the class path, therefore this shouldn't be included in the resulting build. Let's run it one more time. Okay, check out the Java class one more time, and you can see that there's no mention of our demo configuration. It was pruned from the output. So this is just one example of the power of the AOT framework, is that we can do transpolations on the code before they get fed into the GraalVM native image compiler. You'll see that we're going to do a lot of interesting things with the Spring AOT framework. One interesting possibility. So now let's create a new project. We'll use Gradle. We're going to use Spring Native. We're going to just call this Gradle build. And so the goal here is to develop an application that uses Gradle to create a local binary on my host machine as opposed to a Linux binary inside of a Linux Docker image inside of a container. Maybe you just want the build. Maybe you have some other process whereby you get the Docker image. So we'll hit generate. Open this up. Okay, there's our build, our application. Let's just open up the code here. And we're going to create a public static void main. You know, I just want something to print hello world, as is the custom. Okay. There's our application. We're not going to use anything in particular here. The focus is more on how to take our existing build and turn it into a GraalVM build. So we have these dependencies here. We need one more. We need the GraalVM plugin. Version. Okay, so we've added the GraalVM build tools native plugin. Now we need to make sure that we have the right repositories. So I'm going to add Maven local because I've done a local snapshot build. I'm going to add a bunch of other things as well for the published snapshot repositories. I'm going to leave basically everything else as is. The only thing that remains is to change the settings. Okay, so we'll go to settings.gradle. And just as I did before, I'm going to add all those repositories. All right, that should be it. That's all I need to get started. All right, we've got our build. Let's go ahead and use it. We're going to go ahead and run the tests as native tests, and then we're going to run the build. So there's two different tasks here. Recall that with Maven, you have one lifecycle phase to which only one thing can be mapped. If you want to switch what gets mapped to it, then you need to have a profile, which is basically a set of behavior that only activates when you activate a profile by passing in a command line switch. And so in that way, you can remap things to the particular phases, which makes sense for Maven lifecycle sort of workflow. But for Gradle, it's natural just to define arbitrary tasks and arbitrary steps, and so those can, they can help differentiate themselves in their naming. So instead of using test and build, we're going to use native test and native build. Let's do that. So we'll say native test and then native build. Now this is going to compile the test. This is a new feature in Spring Native 0.10.0. This is a new feature that allows you to run your tests not just in the JVM, but as native code compiled using GraalVM and run in that context. As you've no doubt learned thus far, compilation inside of Graal is not the same as compilation on the JVM. There are some substantial differences between those execution contexts, and so running tests in that context is critical to being confident that what you've written will work in the production environment. So let's go ahead and kick off this build. All right, the build is finished running. We can see if we scroll up that the application itself has been compiled, but also the tests is the actual tests themselves running in 61 milliseconds. That's not bad. And then here's the actual application, the whole compilation, etc. And we can look at the actual binaries if we go to the native image folder, Gradle, and then we can see that. And here we have the native tests, which is the binary we can run again, which is kind of cool to run the tests. And then we have the Gradle build. So let's go ahead and run these. First, the native tests. Okay, they're done, 32 milliseconds. And then the build itself, the actual application, 26 milliseconds. Not bad. And so that, my friends, is how you create a Gradle-based Spring Native application. All right, this time we're going to use Maven to do a local build. We're going to call this the Maven-build. We're going to bring in Spring Native, and I'm going to hit generate. So as always, we'll have a little runner. Okay. Now we need to change our build. So let's go top to bottom and kind of review some of the changes. First things first, we're going to set up a plugin management section to configure our plugins globally. The first plugin that we're going to specify is the Spring Boot Maven plugin. Then we're going to specify the GraalVM Maven, the GraalVM build tools native Maven plugin. And then finally, we want to set up a profile that will run when we want to do a native build. So normally you would have one phase, for building and for packaging and for testing and for things like that, and you can assign one thing to it. The only way to bifurcate that, to partition it, is to introduce a profile so that you can remap certain things to certain phases. So here we're going to create a native profile. Now, interestingly, this JNet platform native dependency comes from the GraalVM build tools module, but it'll eventually be in JNet itself, so it won't be needed as of JNet 5.8. Okay, so we have now our profiles. We've got our profile. We've got the right repositories on the class path. Let's now recompile the application, this time using the profile. So -p to activate a profile, and then the profile is called native. Then we're going to do package, and this is going to run both our tests in native code and our application in native code. All right, the application is built. Let's see what it gave us. So if we go to the target directory, we've got our Maven build. Good, 27 milliseconds. And our native tests. All right, so with that, we've managed to configure our build to compile an application natively. The application itself is very small, 41 megs. That includes a Jerry, a web server, embedded database, everything, right? That's the entire application. You can put that in a container and deploy it, and that's everything that's required to run that. Now, granted, this is a Macintosh binary, right? So if I go here, Unix executable file, that won't run on just any operating system though, right? You can try, but it won't, right? It's a architecture-specific binary, but you know that. We're going to look at some of the ways that we can extend Spring Native beyond the defaults that are provided out of the box. Now that we understand some of the basics of how it works, let's look one step further at how you can integrate it into your code if you should ever need to, or at the very least, so you can understand what Spring Native is doing. Let's build a new application. We're going to call this application Hint. And we're going to just bring in the Spring Native dependency here. We don't need the reactive web. We'll hit generate. Recall what I said earlier. When you compile an application with Spring Native, it creates the configuration that gets passed to the GraalVM compiler through the Spring AOT framework. So we can contribute custom hints, custom bits of information that should be included in that resulting build. One way to do this, beyond using some of the standard supported JSON files for GraalVM itself or the command line switches, is to provide annotations, is to use the Spring Native annotations. For example, suppose I wanted to provide a command line switch to my native build. I could say native hint options enable HTTPS, right? And so this will actually get passed to the generated options to the GraalVM compiler. let's see how that looks. If we can inspect the generated target directory, we can see that in the classes, in the meta-inf directory, in the native image folder, there's a native image properties line file, and that file contains enabled HTTPS. If we remove this and then rebuild, we'll see that that line is now gone, right? So this annotation contributes directly to our ability to compile our application with GraalVM. The native hint is the centerpiece of all the annotations that are provided by Spring Native. Native hint, in turn, supports a number of other interesting things, like a trigger. And this is a thing that you can specify. It's a class that you compiled your code against, that you linked against, but that may or may not be available on the class path at runtime. You probably won't have this use case. Indeed, for most of the hints that we're going to look at, you probably won't need to do this. This is why I would think of this stuff as more advanced. It should be the case that you don't need this most of the time. And if we've done our job right, then you won't need this stuff most of the time. But if you do need it, it's nice to know you've got it. So this particular trigger activates when a type that you want to link against is on the class path. So let's say JDBC, I'm using this one, right? The trigger activates when this class is on the class path, or, as happens to be the case here, when this auto configuration is perceived to be true at compile time, right? So here we would test for the presence of data source in JDBC template.class. If these types are, if this condition is true, then this trigger will be true, right? It doesn't, the GraalVM compile time analysis can't determine all of the conditions that Spring Boot is aware of, but certainly the presence or lack of a presence of a class we can detect and act on. And for any other class that's not an auto configuration, the mere presence of it will result in this trigger being true. And if that's true, then all the annotations, all the attributes that you specify here are also applied. And there's a lot of other things that you can specify here. Now, you could specify them in this annotation. Like you could say, okay, I want all my serializables to be in this attribute, right, etc. All these attributes, all the serializables would be in this attribute and so on. And so you can have these things activated based only on this condition, and that's fine, right? These things can also be provided on top of the class, and it can be any configuration class, any native configuration class, and of course your Spring Boot application. So we're going to use some of these hints directly. We're going to take a look at some of these use cases that warrant their use. Remember that there are several things that GraalVM does not like, things that will cause it to compile an application that we cannot use at runtime. Things like serialization, things like Jdk proxies and AOT proxies, things like reflective type access, things like JNI, etc. So these things are things that you need to care about if you want to have your application compile successfully. So let's take a look at some of these use cases. The first thing that we're going to look at is loading a resource. When I say a resource, I mean something like application.properties or a internationalization bundle or something like that that lives in the jar that isn't a class file. It turns out that this is pretty hard to demonstrate because Spring Native does a pretty good job in most cases. So if you have something in resources and you've got a file in there called application.properties, or if you've got an image or whatever, all of that gets baked into the native heap, and so it'll load correctly no matter what, right? You don't have to provide a custom hint. It only gets useful if you have stuff outside, right? Where I noticed this is useful is if you have a custom resource located in the resources directory of some other jar, right? Or if it's at the root of some other jar. So let's go to our build here. And I'm going to add a dependency that I created earlier. Let's called library with resources. And it's just a library that I have on the class path on my local machine. I went to start.spring.io, created a new project, and all this project has, when you open it up, is a folder at the root called data and another one called airline safety.csv. This airline safety, I think, came from an online data set. It doesn't really matter, right? It's just a file in another folder. And so if I wanted to read that, well, then I'd get into some trouble, right? So let's look at that as an example. Okay, so we have this library now on the class path. Let's read it. So we're going to create a runner to read the data. Application runner, resource runner. And we're going to read the data as a class path resource. So class path resource equals new class path resource. And we're going to then read it into a, by the way, did you know you could have this injected? So class path data resource CSV. And we're going to say try csv dot get input stream var in equals. Okay, so we're going to read that data. I'm going to say new file input stream reader, new input stream reader. Contents.split. There are, lines.length lines. Okay, so let's run this, and clearly on the JVM, this should work. Okay, there are 57 lines. And if we go down here, 57 lines, so it checks out. Let's now turn to the native image compilation. Maven clean package, Spring Boot build image. And you can see it complains because it says the file data.lnsafety.csv cannot be opened because it does not exist. All right, now we can fix that with a very easy resource hint. And it asks for the pattern. And we're going to just give it the actual path, and recompile with that in place. Okay, the build is finished. Let's try running it. And you can see that time we got 57 lines, so it's worked. The next hint we're going to look at is the serialization hint. Here, we're going to create a simple example that serializes some objects to their bytes and then writes them out. Why would you want to do this? I can't even imagine. I don't know why. I wouldn't do it. I haven't done this in years. Actually, the only time I've recently encountered this was with Quartz. I helped write the Quartz support for Spring Native, and one of the things it does is it actually persists. It does serialization, Java serialization. So it's a thing. It's a thing people will do. Hopefully you don't encounter it. You won't encounter it. At least you shouldn't with Quartz because we already built that support for you. But if for whatever reason you have a thing that's doing serialization, then you're going to care about this hint. So let's create a simple example here. Application runner serialization runner. Turn new application runner. And we'll say output equals, and we're going to write this. We're going to write out the bytes, right? We're going to say user.home output, okay? And this is going to be a file. So there it is, resource output directory. Okay. I'm going to say output directory .get file. And here we'll say try var out equals new object output stream and new file output stream output. Okay, so we're going to create an object to write out to the file. And so here I'm going to create a custom type just so we have something to serialize. Okay, so we'll say class customer implement serializable. And we want it to have getters and setters and all that. So I'll bring in Lumbach. Okay, I'm going to give it a integer ID, a private string name. Okay, so we've now got our basic serializable object. Let's try this out. So we'll say var customer to write or written. There you go, new customer 1 Jane. Okay, so we're going to say out dot write object written, and that's it. That's the entirety of the write logic. We're going to then read it just to prove that it works end to end, right? So var in equals new object input stream, new file input stream output. And here we want to read the same data. We want to read read equals in dot read object. There we are, customer. And want to say system out read wrote written. Okay, good. So there's our basic serialization. Silly example though it is. Let's try it out. Okay, so now if we go to the console, cat output, you can see I've got this customer here, Jane, string, etc. Okay, so now it's working. I'm able to write the data and read the data. Let's now compile this using GraalVM. Okay, so we've built the application. Let's run it. And clearly it's failing because we can't serialize this particular type, right? And it's even kindly given us the hint that we should add something to the serialization configuration, which we're going to do in a roundabout way using the serialization hint. Once added, we can recompile. The application is built. Let's run it now. And there we go. You can see it's worked. All right, in this section, we're going to look at a different hint. This one's supporting reflective type access. Now again, you're probably not going to use this. You're probably not going to need to know about it. But if for whatever reason you want to do reflective type access against a type without ever having an instance of that type or ever importing that type in your code, and again, the use cases for which that is a scenario are vanishingly small, and the use cases for which that's a scenario for which there isn't already something out there that can do it for you, like Spring, again, almost nothing. But should you have that use case, or you want to integrate a third-party library that does some such things, then it'll be very useful to know about this particular hint, called a type hint. So we're going to create a type here, simple customer service, and we'll have a method called find by ID that'll take an integer. And I'm not going to talk to a database here, just something very simple. Math.random 0.5 John. Okay, so there's my simple class. Let's create a reflective runner. And the goal here is just to get an instance of the class. But of course, that's actually a lot harder than you would think, because what I need is to not import that type, right? What I want to do is I want to demonstrate that this won't work, but the thing is, it might work, actually, right? GraalVM is really smart. I could be wrong, I could be mistaken, but I'm pretty sure that when I pass in a string class name into a method like class.forName, I get, like if I just pass in the string literal, just directly, but I'm pretty sure that actually works. GraalVM is really smart. It understands that that string couldn't possibly be anything besides a type, a type path, a fully qualified name for a type. So typically, in order to make this demo work, I obfuscate a little bit. I introduce string concatenation and that kind of thing. Maybe even an intermediate variable like, period or whatever. And again, I could be wrong. I confess I haven't given this the rigorous scientific examination it deserves. But again, who cares, right? You shouldn't have to break GraalVM. That's not the goal. The fact is that it'll work a lot for you out of the box, but sometimes it won't. And so we use it, and you can use it as well. So let's take a look at how to use it. We've got a class. Now let's create an instance of that class. Get declared, or get constructors. Let's get all the constructors. Get the first one, create a new instance, and that doesn't require anything in the constructor. And then I want to get a method. Method equals class dot get declared method, find by ID, int dot class. Okay. Oops. Int dot class. And then finally, we're going to invoke that method on the instance. So instance, and we're going to say, let's say 8. Okay. Var result. I'm going to print out the results. So result, and voila. Let's go ahead and run this and see what we get. Oh, index out of bound. I bet that's this constructor's business. Declared constructors? Oh yeah. That's what I needed to do. It's not public. Okay, so that's worked. Clearly, I've gotten the result. ID 8, name is Jean. Okay, good. So now I want to see if that works in GraalVM. So we're going to go back to our command line and recompile. All right, our application is compiled. Let's go ahead and run it. And you can see it failed. Couldn't manage the reflective access for that type. It even has a nice error analyzer that gets printed out. Native reflection configuration 4 is missing, and it suggests that we might contribute that configuration using one of the supported mechanisms, which we're going to do. So thanks for the hint. What we want to do is add a type hint. Okay, and the type hint has a lot of fields here. You can be very specific. You can say I want to give it a class literal. If you have a class path that's on a type on the class path that may not be there at runtime, or you can give it a type name, right? Which is what we might do here. So hints dot simple customer service. You can also be very granular. You can say, okay, I want access bits dot all, right? You can see there's lots of options for particular fields, full reflection, whatever. Just to be safe, I'm choosing all for this type. You can also be even more granular. You can say that you want for this field, right? This field expects a field hint, and that could be field hint, and allow unsafe access is true, allow write is true, name equals foo, and that would be a field or name or something, But obviously, we don't have a particular field that we care to open up. It's just we want to be able to call methods and stuff, so we don't care about that. But you have lots of granularity, lots of support there. And remember, this can be used in conjunction with other things. So with that in place, let's go ahead and recompile the application. All right, our application is finished compiling. Let's go ahead and run it. And there we go, it works as we expect. So one little hint brings back reflection, great. The next two hints that we're going to look at are related. The first is Jdk Proxies. Now, the Jdk has a mechanism whereby you can create a type that looks like a type. Basically, it's a wrapper or a thing that has a facade. And you've seen this before. You've seen lots of great uses of proxies before as a design pattern, right, from the Gang of Four book. It's a design pattern that is designed to give the client of a type a face, a facade that it can use to interact with something that may not actually be a live object. It might be something else. So you could create a proxy that when you invoke methods on it, it actually translates that into web service calls or RSocket calls or whatever. So if you've ever used Netflix's Feign in Spring Cloud, or if you've ever used a RetroSocket with RSocket, then you know what these things are, right? So a facade is a very useful design pattern used all over the place. Proxies are very useful as well. And the Jdk even has a mechanism that you can use to create your own interface-based proxies. So let's take a look at that. So we're going to create a interface-based proxy. And we're going to create a invocation handler. And the invocation handler is like an event handler. It's a callback for method invocations against our interface. And so we're going to need to then have an interface that we want to use. So let's create a order service interface. Okay, we can say void cancel order. Okay, so that's our interface, and we want an object that implements the interface but does something that we can control. So we'll say once that's done, let's create a proxy for it, but we need to have the class name. And again, you know, the GraalVM compiler is pretty smart, so I need to do a little bit to do something so that it actually breaks, right? Because otherwise it might actually work, which is not what we want in this case. So order service. Okay, and we're gonna var equals class.forName, class name. And now we want to be able to create a proxy out of that. So proxy equals proxy dot new proxy instance class loader, new class class, and of course here's the invocation handler. Okay, so that's our proxy object that if we wanted to, we could cast to the interface, to the order service interface. Let's actually use that. So we can go through the interfaces for var I in proxy.get class get interfaces, I guess. You know, let's print out interface found I.get name. Okay. And we can also call methods on it. So we can say var method equals class dot find, get declared method cancel order, and we say method dot invoke on the proxy instance, and we should see something happen. Now, of course, what happens is up to what we program here in the invocation handler. And so we want to handle that one particular case, that very special case of when somebody invokes that method. Then system out, you want order args. Oh, you know what? We need a parameter for this to be meaningful. Let's actually add an int order ID. Okay. So here now it's int.class, and now you want to say you want order number args canceled. Too bad. And then we just return null. Okay. Otherwise, we just forward it on to the underlying thing, which is, you know, it's not going to work. There's nothing there, but we don't have any answer for that, you know. But you can see how this would work. You get access to the name, and you can provide the response. So you can, in theory, you can just forward the invocation for everything, and then wrap it with some cross-cutting kind of concern. Okay, so that's our JDK proxy. Let's see if that works. So what we've done is we've dynamically looked up the name of a type, an interface on the in the class path. Then we've created an invocation handler that listens for a particular method on that interface. We've gotten the current system class loader, and we've used a JDK type called proxy to create a new proxy instance. Then we're just sort of using that proxy reflectively. We're invoking methods on it that we assume will be there because it implements order service, and we're visiting the interfaces that are on that proxy instance. Let's see what happens. Wrong number of arguments. Oh, yep, right. I'm going to pass in an argument here. So let's say 29. Okay, it says you want order number 29 canceled. Too bad. Now let's compile this as a GraalVM application. All right, the application is compiled. Now let's run it. And you can see that native reflective configuration is missing. And of course, if we had that, we still wouldn't be able to proxy it. So in order to fix that, we'll add a proxy hint for the JDK, a JDK proxy hint. So we'll say at Jdk Proxy Hint, and you can just put the type as a string, as always. Now we've got our proxy hint. We also need to add a type hint so we can reflectively access the resulting type. So same as before. All right, so these two could go together, right? You could actually say that we have types, and then we have proxies. And voila. So with that done, let's go ahead and compile the code. Okay, the code is compiled. Let's go ahead and run it. There you go. So now we've got a interface-based proxy working in GraalVM. There is another kind of proxy, however, and it's not natively supported by GraalVM because it's not something that's natively supported by the JDK. And that is to say, we have a class-based proxy. This is a thing that changes from one framework to another, but the basic idea is instead of having the JDK use proxy.newProxy instance to proxy an interface, what if we could proxy a class, a concrete, already existing class, so that we could decorate it with some extra functionality, right? Maybe each method invocation gets logged, or a transaction gets started and then closed on the finish of the method, or maybe each method results in a network call or whatever. These are the kinds of things you want to do when you have a framework, right? And so it's useful not just to have a facade or a proxy for an interface, but also for concrete classes, such as when we apply aspect-oriented programming to concrete classes. And this is a Spring-specific thing. The approach is based on the idea that we're going to subclass dynamically a type at runtime. So we basically create a new class by subclassing an existing one, and then in that subclass, we dynamically write the code that introduces the cross-cutting concern before and after the invocation of the parent class, right? So it's like you're calling super, but before you call super, you do something else, and then you finish it, right? So you can actually decorate the invocation. You can actually intercept the invocation, get the arguments, process it, etc. So this class-based proxy is supported through things like CGlib or ByteBuddy or whatever. And the point is, we were looking for a way to support that. There is no JSON file that supports class-based proxies in GraalVM, but we do have a hint that you can use. So let's take a look at that. We're going to create a new runner here called AOT Proxy Runner. And we're going to create a concrete proxy, right? So here, we'll have a class called concrete order service. So this is actually a class with types, methods on it and so on. We'll have public void cancel order, int order ID, canceling order. All All right, so there's our concrete type. And let's go ahead and set this up. So same as before, class name equals all right, so there's our class name, class, and then we're going to create a class instance. And then we want to actually create we want to create an AOT proxy. So we're going to need a target, and the target is the concrete instance that you want to decorate, right? So the fundamental business logic is there, but we want to create a class that subclasses this, that wraps that instance. So we're going to use the Spring Framework Proxy Factory Bean. The Proxy Factory Bean allows you to introduce advice, and we're going to get back to this in a second, but it looks very similar to our invocation handler for Jdk Proxies. We're going to introduce the target, which is this instance here, and we're going to say we want to proxy the concrete class. Yes, please. All right, and then finally we can actually get an instance. So get object var proxy, and we'll get a method equals class dot get declared method cancel order, and we're going to call method dot invoke on the proxy instance, right, and pass in 42. Okay, so we should see method invocation delegating to the underlying thing. That's what I'm doing here, is I'm saying go ahead and forward the invocation to the underlying target. But before I do that, or rather as I do that, I want to decorate the result, okay? So we're going to have a little bit of logic here. We're going to say, okay, when each method gets called, we're going to print out equal signs 1, 2, 3, 4, 5, 6. Okay. After this has happened, we want to print out minus signs. So 1, 2, 3, 4, 5, 6. Okay, so there we go. And all we're doing is we're delegating to the underlying thing, but we're decorating the invocation, right? So now we can say return result. And of course, with a void method, there is no result, so this will just be null, but that's okay. It's part of the contract, it's just return. Okay, so there's our advice, our invocation handler, if you will. But it's basically going to delegate to this underlying concrete type. Very convenient, huh? So now we need to run it. Let's just see if it works. Okay, see, I called cancel order on the underlying thing, and it printed out it wrapped the method invocation with these framing lines. It's a silly example, but you get the picture, right? We're calling methods on the object doesn't know about this thing, and yet we're able to introduce it. This is the benefit of a concrete class, of a proxy like this. And we use it all the time in Spring. So for example, if you do pre-advise or pre-authorize and things like that on web endpoints, REST controllers, that kind of thing with Spring Security, that uses class-based proxies, right? When we do Java configuration, we use class-based proxies. AOP, just if you want to write an aspect and you're not using low-level stuff like the Proxy Factory Bean or Jdk Proxies, that will use this kind of class-based proxy. So this is a useful thing to have, but it's one thing for which there is no, like I say, there's no equivalent JSON configuration for GraalVM itself. We support this as a hint. So in this one regard, it's asymmetrical. Let's go ahead and compile this application as a GraalVM native image and see what happens. Okay, the application is built. Let's run it. And you can see it blows up catastrophically. But it is nice enough to tell us what we need to do. Class proxy missing at runtime, hint required at build time. AOT proxy hint. So let's just go ahead and plug that right in. And you can even tell, you can see that there's some nuance to the kind of proxy that it is, and so we support different things here, but it's fine. You can determine what works best for you. It's a whole other discussion, but we're going to leave that there. We might, because we're doing reflective access, we might also want to have a type hint for this. just as before. Okay, so there's this. It's called concrete order service, isn't it? Let's go ahead and rerun. It's compiled. Let's go ahead and run it. And there we are. It worked. We got our proxy, our class-based proxy, our AOT proxy working out of the box. Thus far, everything that we've seen is using static fixed annotations. We're going to go ahead and introduce the native configuration API, which is a dynamic programming model that you can use to write programmatically your hints for your Spring native applications. You can then package that up and distribute it in your organization, and it can get involved into any of the code you want in the same sort of automatic way that Spring Boot's auto configuration works through the smart use of a service loader. So let's go ahead and create a new Spring native application. I'm going to call this external or reusable hints. So reusable hints. I'm going to add in the native support. And that's it. We're going to hit generate. We'll open this up. Okay, it's open. We're going to add one more library to this. And so we need the Spring AOT module as well, not just Spring Native. And now we're going to build our own hints library, but it's a regular jar, not a Spring Boot so-called fat jar. So we need to disable all of this actually. Don't need any of it really. So let's go ahead and get rid of all this. And we're going to create a hint that programmatically registers the order service proxy hints. Okay, extends native configuration, and this type doesn't exist because I have neglected to refresh my Maven build. Let's reload. And voila, it implements native configuration, which has this method called compute hints. And in that, you can return a list of hints, hint declarations. So I'm going to return list.of HD. I'm going to create HD to be a new hint declaration. And there we will add the dynamic behavior we want. Now, what I'm going to do is I'm going to create a hint for the order service class name. Example.hints.orderService. And I'm going to say hd.add dependent type, and we want the order service class name, and we want to say that this has the new access descriptor of access bits.all. We want to add the proxy descriptor, new Jdk proxy descriptor. And here's the list of types, so list of order service class name. And then finally, let's just print it out. Adding or registering reflective and proxy hints for order service.class name. Okay, so is this doing anything special? No, we've already done this with the annotation. But the point is you could do a lot of different things here, right? You have access to this type system. You can say resolve this type called, whatever this. We can keep this up here. And you can actually use that. You can say order type. This is kind of like the reflection API in Java, except it's at GraalVM compile time. So there is no runtime reflection in this case, but it's a meta model that lets you kind of check things like, which packages does it belong to, find annotations, giving them methods, that kind of thing on a given type. And you can then inspect it. And this is great if you want to do really dynamic frameworky type things. For example, that whatever framework you're using looks for all these types based on this particular combination of things, maybe an annotation, maybe an interface, whatever, and you can do the same trick here. You can find all those types and then treat them in a certain way, give them the right hints so that they do the right thing at runtime. So this is very convenient. Let's package this up for reuse now. We need to create a new directory in the resources directory called meta-inf services. And in there, we're going to put a file named for the kind of service loader that we want to use. So here it's org.springframework.nativex.type.native configuration. And so this, of course, is our native configuration class. I'm going to put that in there. All right. So there's our configuration. And with that done, we can now package this up. We can compile it. Maven clean install. Remember, this isn't going to be a native image. This is just a regular jar, but it needs to be on the class path for the GraalVM compilation. We have no tests. We should, but we don't. Okay, so now we can return to our hints project, and I'm going to add our GraalVM native dependency there. So we call this reusable hints. And we can go to the AOT plugin. Here we are. Dependencies. Okay. Now let's rebuild this after we've commented out the order service hints that we explicitly added earlier. So we're going to get rid of this one. And we're going to get rid of, actually that's it. We're going to get rid of that, right? That's all. Okay, let's restore this. Let's rebuild it. Even. Okay, the application's compiled. Let's go ahead and run it. And it worked, right? Same thing, except that you'll notice that when we ran the application and we compiled it, you can see it says generating a class for when we compiled it, we can see our custom hints in play. Registering reflective and proxy hints for COM example hints order service. So it invoked that at compile time to decide how to register these hints dynamically, and those got fed into the application, and everything worked just as though we had registered the annotations directly. This is nice because now you have a way for your modules, for your libraries, for even if you have an organizational standard and it's some third-party thing and it hasn't been already supported in Spring Native, now you can do the same thing. You can support it yourself in a way that's consistent with what people are expecting, right? It just works. You don't have to do anything. So hopefully that'll get you to where you need to go. There's a lot of other SPIs in the Spring Native ecosystem that you can use above and beyond native configuration. I just find this one to be the most generic and useful.
And with that, my friends, we've come to the end of our journey. We've looked at most of the hints, but not all of them. And there's certainly a lot of other possibilities here, but hopefully you've got a feel for how you can help Spring Native take your applications to GraalVM and help them, and to help make that process easier, not just for your own applications, but through the use of dynamic native configuration and other types that we didn't even get a chance to look at, like component processors, to make it easier for everybody else to also take their applications to GraalVM. Obviously, this has just been a superficial sort of what you need to know to understand Spring Native kind of look. There's a lot more that could be said, and I suspect will be said. Hopefully you got something out of this. Thanks so much for watching as always, and we'll talk to you next time.